All right, Physics 20s. So today we're just going to go back through a couple of examples from class today, a couple of the sort of simpler ones just to start you off on these problems with work and energy and the connection between work and energy. So first we have this example that I said we needed to correct. It was handed to us described as this, where we've got work is done on a lazy cat by pushing it 54 centimeters across the floor with a constant force of 50 newtons. And I said, well, we needed to test that. So I took my cat, that's Toby being dragged there, and I dragged him across my kitchen floor. Let's just watch the experiment once. Looks like he's in some discomfort, but he really didn't mind all that much. It's really not that bad. But that actually measures the force for us. So as we're pulling it along, wait until it kind of gets pretty constant. Right about there, we'll pause it. So it looks like we've got about 10 newtons of force. Let's write that down. So about 10 newtons of force being applied pretty consistently to drag him across the floor. I also measured the distance that we traveled there. The distance itself, it wasn't 54 centimeters, probably closer to 240 centimeters. And to figure out the amount of work being done, because that's what the question's asking. The question's asking, what is the work being done on the cat? Oops, that's the previous example there. So the question's asking, what is the work being done on the cat? We need our formula, right from our formula sheet, of work equals force times distance. And so we have the force, we have the distance, so it's just a matter of multiplying those together. So work would equal 10 newtons multiplied by the distance in meters, 2.40 meters. And so we're looking at about 24 joules of work. 24 joules of work. Okay, next example. An 8-kilogram wagon moves along a horizontal sidewalk at a speed of 15 meters per second. Its wheel falls off, and now it has a frictional force opposite the wagon's motion, which brings it to rest in 2.0 seconds. Determine the work done on the wagon. So in this case, the work being done on the wagon, that's what we're looking for. And that is due completely to friction. So that's the work due to friction. That's what we're looking for. We're given some information in the question. We have an 8-kilogram wagon, so we know the mass is equal to 8 kilograms. We know that it has a speed of 15 meters per second. And that's kind of all we know about it. We know when it comes to rest in 2.0 seconds. Time to rest equals 2.0 seconds. And so if we want to figure out the work being done, we would go work equals force times distance. But we have a bit of a problem. We don't necessarily know either of these values directly. To figure out the force, we need to figure out the force due to friction, which isn't immediately obvious here. We would need some more, we need to solve that as well. Also the distance as well. We're not told how far it takes to come to rest. We know it takes 2.0 seconds, but we don't know what that distance is. So to solve it this way, we might be able to do it, but it probably takes a lot more work. So let's not worry about that just yet. Let's try it a different way. Because we do have another formula for work. Work is equal to a force exerted over a distance, but work is also equal to our change in energy. And the change in energy here, just to describe it, we have energy that is in the form of kinetic, because the wagon moves along a horizontal sidewalk. The fact that it's moving means that it has kinetic energy. And when it comes to rest, that means we have 0 kinetic energy. It means it's all gone at that point. So our energy goes from kinetic to 0. Now it can't just go to 0. It actually has to turn into something else because energy can't be created or destroyed. So it doesn't really go to 0, but that goes into the work done by friction, because the work is equal to our change in energy. This is our formula from our formula sheet. This is the one we're going to use. And that change in energy converts all of the energy we had in kinetic into work done by friction. So our energy initially is kinetic. We know that is equal to 1/2 times mass times its speed squared. 1/2 times 8 kilograms times 15 meters per second squared. All of that together. When you put it into our calculators, we should get 7,200 joules. And so that's 7,200 joules. That is the amount of work done by friction to bring this cart to a stop because it had to start with that much kinetic energy. That's where we'll stop right now. There are more examples. There are more practice problems in the notes. So feel free to try those at your will.